Okay. So, from here we finished from here, right, in the previous lecture. So, now replace P by S, you have delta psi f d will be k 3 upon 1 plus S T 3 in bracket delta E f d minus k 4 delta delta. This is equation 271, right. Next, after this block diagram is drawn. Now, here if you see that delta psi f d, right, is equal to, just now we have given no k 3 upon 1 plus S T 3 into your what we call k 4 delta delta, your delta E f d minus k 4 delta delta. Here the delta E f d field voltage, that E f d is constant, right, then your delta E f d will be 0. That is why I have just made it delta E f d 0. You forget about this one for the time being, right. It is basically delta E f d minus here the entry point is k 4 delta delta, right, k 4 delta delta. So, E f d minus k 4 delta delta into k 3 upon 1 plus S T 3, right, and that is equal to delta psi f d. Therefore, and delta t, whatever you get, it has two component, one component due to this delta psi f d, right, and another component is coming from here, this is nothing but k 1 delta delta. So, this is actually 4 constants so far, we have to make 2 more constants, but later we will see, and this is your delta delta, right. So, this is that your complete block diagram for all these equation in terms of k 1, k 2, k 3, k 4. I think this is understandable to you. This is 271. So, this is the block diagram representation for with constant E f d. Constant E f d means delta E f d is equal to, say here it is 0. That is why it is written, right. So, now we will go to the next page, right. Now, with p psi terms and speed variations neglected, the stator equations are, right. So, now if you go to the your what you call the stator voltage equations, right, because we have to find out 2 more constants k 5 and k 6. So, with p psi terms and speed variations neglected, the stator voltage equations are, it will become actually, if you go back to the stator voltage equations and there you just make this small exercise, you will get E d. So, effect of field flux linkage variation on system stability. Now, from the block diagram, that is figure 27, which your constant field voltage, that is delta E f d is equal to 0, the field flux variations are caused by caused only by feedback of delta delta, right, through the coefficient k 4. Just hold on, right. So, this represent the demagnetizing effect of the armature reaction. This is another question to you, that why it represent the demagnetizing effect of the armature reaction. This is a question to you. You will put in that answer, you put it in the forum, right. The change in air gap torque due to field flux variation caused by rotor angle changes is given by delta t upon delta delta due to delta psi f d is equal to minus k 2 k 3 k 4 divided by 1 plus S T 3, right. Delta t upon delta delta due to delta psi f d. So, let us go to the block diagram. Here, right. So, if you look into that change in your what you call that your just hold on, yes. So, change in your delta t term, right, only because of this delta psi f d, what will be, it is basically it will become this delta E f d is 0, delta E f d is 0 because it is constant, your this is your constant E f d. So, delta E f d is 0. So, it will be your minus k 4 delta delta, then k 2 k 3, this is due to your delta psi f d. So, basically it will become whatever we are writing, that change in this thing, right, it will be basically minus k 2 k 3 k 4, right, k 2 k 3 k 4 and delta delta, because delta E f d is 0, right, divided by 1 plus S T 3. This is the thing, it is input to this point, right. So, that is why if what, and this side, if you think this side it is coming, so k 1 delta delta. So, that is why due to delta psi f d, this is minus k 2 k 3 k 4 upon 1 plus S T 3 delta delta is here. So, if it is so, just let me clear it, right. So, That is why the delta t delta delta due to delta psi f d, because there it was given no, that particular term was minus k 2 k 3 k 4 delta delta upon 1 plus s t 3. Therefore, delta t by delta delta due to delta psi f d only, the left hand side of that block, it is minus k 2 k 3 k 4 upon 1 plus s t 3. This is equation 272. In general, the constant k 2 k 3 k 4 are usually positive. K 2 k 3 k 4 for your what you call for realistic values, they are all positive. So, if k 2 k 3 k 4 all are positive, means this term your what you call numerator term will be always negative, right. So, the contribution of delta psi f d to synchronizing and damping torque component depends on the oscillating frequencies as discussed below, right. It depends on, we will see for s is equal to j omega, then we will analyze certain thing. Now, first part, in the steady state and at very low oscillation frequency, say when omega tends to 0, right, delta T e due to delta psi f d will be minus k 2 k 3 k 4 delta delta, because if omega if put here s is equal to j omega and omega tends to 0. So, 1 plus s t 3 term will become 1. So, it will be basically minus k 2 k 3 k 4 delta delta, right. Therefore, delta t due to delta psi f d, actually just I am making for you, it is something like this, that we are writing delta, I will overwriting on it, delta t by your delta delta due to delta psi f d, say is equal to minus k 2 k 3 k 4 divided by 1 plus s t 3, right. Now, s is equal to your j omega, and omega for very low frequency omega tends to 0. So, this term will become basically minus k 2 k 3 k 4, right. Therefore, we can write delta t due to delta psi f d will be minus k 2 k 3 k 4 into delta delta. That is why we are writing that delta t due to delta psi f d is equal to minus k 2 k 3 k 4 delta delta. This is equation 273, right. Now, next is the field flux variation due to delta delta feedback, that is due to armature reaction. I told you that why it is called, introduces a negative synchronizing torque component, right. So, field flux variation due to delta, because k 2 k 3 k 4 these all constant are positive. So, therefore, that coefficient of delta delta is negative, right. Therefore, introduce a negative synchronizing torque component. Now, the system becomes monotonically unstable when this exceed k 1 delta delta, the steady state stability limit is reached when k 2 k 3 k 4 is equal to k 1. Now, again I have to go back to that your block diagram. Now, this is our block diagram. So, in this case at low frequency, right, when omega tends to 0, the term here whatever it is going, that is your minus k 2 just mathematically k t k 4 delta delta, and from this side it is coming your k 1 delta delta, right. Now, then delta t will be what? It will be basically k 1 minus k 2 k 3 k 4 delta delta, right. Therefore, if this term is equal to 0, this term k 1 minus k 2 k 3 k 4 if is equal to 0, then your k 2 k 3 k 4 is equal to k 1, that is what we are telling. When we are taking s is equal to j omega and when omega tends to 0, right. So, that is why just hold on, that is why we are making this one, that system become monotonically unstable when this exceeds k 1 delta delta. The steady state stability limit is reached if we make k 2 k 3 k 4 is equal to k 1, right. Now, part B, at oscillatory frequencies much higher than 1 upon T 3, right. When you take your s is equal to j omega, right, and omega is much higher than 1 upon T 3, that means 1 plus your what you call j omega 3 is approximately j omega T 3, right. So, that means that is in that time, at that time delta t due to delta psi f d minus k 2 k 3 delta delta divided by j omega T 3. At that time that oscillating frequency is much higher than 1 upon T3, that is your omega is much higher than 1 upon T3 and S is equal to j omega, right. That means 1 plus S is equal to j omega. So, j omega T3, right, is approximately equal to your j omega T3, that is what we have written here, right. So, and that one can be written as you numerator and denominator you multiply by j. So, it will become j square. So, minus plus. So, basically you are writing k2 k3 k4 upon omega T3 j and j delta, right. Now, here just hold on. So, here the delta t due to delta psi f d actually k2 k3 k4 upon omega T3 j delta, thus the component of air gap torque due to delta psi f d is 90 degree head of delta or in phase with delta omega. This one again I am putting a question to you that it is given j delta. So, you just a hint I am giving that bring j delta in terms. So, if you look into that k2 k3 k4 j delta, but torque is a function of your delta, but one j term is there. So, thus the component of air gap torque due to delta psi f d is 90 degree head of delta or in phase with delta omega. So, this is a question to you, you have to bring it j delta terms in terms of delta omega. How to do this? Everything is there in block diagram, just you do this, that is why we call or in phase with delta omega, that means j delta term will become in terms of delta omega also, and that time we call it is in phase, otherwise we call 90 degree out of phase. So, this is a small question to you and just give the reason when you listen to the lecture in the forum, right. So, actually this one small derivation is there 3-4 lines, not 3-4 lines, even 2 lines you can make it, right. So, hence delta psi f d result in a your what you call in a positive damping torque component, just I will go there. So, therefore, because k2 k3 k4 always is positive, omega is positive, T3 is positive. So, it is producing basically giving a positive damping torque, right. So, now at third point, the C, at typical machine oscillating frequencies of about say 1 Hz, that is 2 pi radian per second, delta psi f d results in a positive damping torque component and a negative synchronizing torque component, right. So, the net effect is to reduce slightly the synchronizing torque component and increase the damping torque component. Now, if we make like this, this is my delta and x axis, y axis delta omega and this is delta T e, right. So, this is delta T s, the synchronizing torque component, it is showing negative, and delta, this is actually k2 delta psi f d, that delta psi f d, right, that is your due to your what you call that k2 your delta psi f d, the field flux changes, right. So, this is your delta T d. So, this is actually positive damping torque delta T d and negative synchronizing torque due to k2 delta psi f d, right, and this is your what you call the representation. So, next is, I hope this is understandable, but 1 or 2 questions I have put, right. That is, one is that torque is in phase with delta T, that due to delta psi f d is in phase with your delta omega or is leading 90 degree from delta, that is j delta, right. So, effect of now excitation system. So, so far we have seen your how many constant we have seen, that your k2, k3, k4, right. So, next we will see that effect of excitation system. The input control signal to the excitation system is normally the generator terminal voltage E t, and we know that E t tilde is equal to E d plus J E q. This we have seen again and again. Therefore, magnitude, if you take magnitude, we know also E t square is equal to E d square plus E q square. Now, analysis of a small perturbation, we may write this equation that, so I mean it is something like this. I mean, when you take small perturbation, say initial value was there. So, E t is equal to say E t 0 plus delta E t, right. Similarly, your E d is equal to E d 0 plus delta E d. Similarly, E q is equal to E q 0 plus delta E q, that is here and here we have substituted. Now, what you do, you square it and simplify. but your small perturbation term square neglected, that means these terms have been neglected. Delta E t square, it is very small, neglected, then delta E d square also neglected, and delta E q square also neglected, right. These terms have been neglected. So, and you simplify, then you will get this thing, you will get delta E d is equal to E d 0 upon E t 0 delta E d plus E q 0 upon E t 0 delta E q. This is equation 275, right. Now, in terms of the perturbed values, equation 246 and 247 may be written as. So, I suggest you go to equation 246 and 247 and just take the small perturbation value. Look, now it is 275, again and again I am not going back, but these notes will be available, just you open those equation and take the small perturbation. I am writing the final one. Therefore, delta E d will become minus R a delta I d plus L L delta I q minus delta psi a q, right. Similarly, delta E q will become minus R a delta I q minus L L delta I d plus delta psi a d, right. So, by using equation 258, 259, 261 and 262 to eliminate delta I d, delta I q, delta psi a d and delta psi a q from the above equations in terms of the state variables and substitution of the resulting expression for delta E d and delta E q in equation 275 L, right. So, basically you will get delta E t, you will get in k 5 delta delta plus k 6 delta psi f d. That means, this delta E t expression is there, right, but we are trying to find out that delta E t terms into k 5 into delta delta and delta psi f d. So, two more constants have been introduced, k 5 and k 6. So, what, but here to I suggest you do it once the way it has been given here, right. So, delta E t you have to bring in terms of delta delta and your what you call delta E d, right, psi f d, right. So, what you have to do, use equation 258 to 262 to eliminate delta psi a d, delta psi I q, delta psi a d and delta psi a q, and from the above equation in terms of the state variables and substitution of the result of expression for delta E d and delta E q in equation 275. This will give you k 5 delta delta plus k 6 delta psi f d. Now, expression for k 5 is given here. So, it is E d 0 upon E t 0 minus R a m 1 plus L L n 1 plus L a q s n 1 bracket close plus E q 0 upon E t 0 in bracket minus R a n 1 minus L L m 1 minus L a d s m dash L a d s m dash L a d s dash m 1. This is equation 277. If you simplify and do this, you will get this is the expression for k 5. Similarly, for k 6 you will get is equal to E d 0 upon E t 0 in bracket into minus R a m 2 plus L L n 2 plus L a q s n 2, right, plus E q 0 upon E t 0 in bracket minus R a n 2 minus L L m 2 plus L a d s dash in bracket again 1 upon L f d minus m 2 bracket close and bracket close. This is equation 278. These expressions you need not remember, k 1 through k 6 if anything is there, all data will be supplied, but I suggest you just derive once, right, just you derive once. So, this is actually equation 278. Now, we will consider the excitation system model shown in figure. This thing, this is k 5 k 6 we have made delta E t, but that will be added in the block diagram, but before that, after that we will take a excitation system. Now, we will consider that excitation model shown in figure 26, right. Here you have a terminal voltage transducer, is that input to this is E t and its time constant is t suffix capital R, that is 1 upon 1 plus S t r. Output is a V 1 and this is a reference set point, reference voltage, and this is V 1. Then exciter is there, we are taking just a gain only, right. Your what you call, you have taken IEEE type ST1 exciter and just represented by gain. Different type of exciters are there. If time permits, then I will cover, right. So, and then output is field voltage EFD, but it has a limiting value EF max, but EF min. But for this course, those limiting thing and simulation we have no time to do that, right. We have to only think about the classroom exercise. So, this is exciter and this that means your in general EFD will be actually is equal to V reference minus V 1 into K is equal to EFD, and V 1 is equal to your Et upon 1 plus STR, right, and TR is the time constant of the terminal voltage transducer. This basically TR is very small, right. So, this is thyristor excitation system with automatic voltage regulator, right, and this is IEEE type ST1A excitation system, only we have considered the gain K of the exciter, right. Now, parameter TR represent the terminal voltage transducer time constant. Now, from figure 29, from this figure you can write that delta V1 is equal to delta Et upon 1 plus STR, because V1 is equal to Et upon 1 plus STR, we are making it P and S same actually, right, that is P is equal to your d by dt is equal to S. So, there is no confusion at all, right. So, delta V1 is equal to delta Et upon your 1 plus PTR, right. So, using this part of value, because V1 is equal to Et upon 1 plus STR. So, delta V1 is equal to delta Et upon 1 plus STR, or you can write that P delta V1 is equal to 1 upon TR delta Et minus delta V1, right. Now, question is that we got the expression of delta Et, that is K5 delta delta plus K6 delta psi FD. So, you substitute that expression, that is from equation 279 and 276. At 276 delta Et is given, that is your K5 delta delta plus K6 delta psi FD, and you just simplify, it will be P delta V1 will become K5 upon TR delta delta plus K6 upon TR delta psi FD minus 1 upon TR delta V1. This is equation 280, right. Now, next is you come back to this equation, right. Now, EFD, I mean if you make it like this, that from the, forget about that min max limiting value, in general if you write that your EFD is equal to your V reference minus V1, right, minus V1 into that K. Now, if you take the small perturbation thing, then it will become delta EFD is equal to Ka, then delta V reference minus delta V1, right. So, this is delta EFD. Therefore, because this thing we will use in the next your equation, right. So, therefore, from figure 29 I wrote this one, delta V reference is not 0. So, this one you should not consider, delta EFD is equal to your Ka into delta V reference minus delta V1, whatever I write, this is actually equation 281, right, because we are not setting delta V reference 0. If delta V reference 0, then this is true, but this is not required, it is actually Ka delta V reference minus delta V1, right. Therefore, from equation 267, and this is your, this equation is 281, what you do, you substitute in that, right, 267, that is the third equation for your delta P delta psi FD. This is the third equation, go back to the matrix of 267, there is a third equation, and there you will, I have written A31, but actually A31 is equal to 0, right. So, see that matrix, actually you will see A31 is equal to 0, but here also I have written A31 is equal to 0, right. So, and if you substitute this thing, you will get in this form, that is your P delta psi FD is equal to A31 delta omega r plus A32 delta delta plus A33 delta psi FD plus B32 delta EFD, but A31 is 0, right. Or if you, or you can write that A31 delta omega r plus A32 delta delta plus A33 delta psi FD plus A34 V1 plus B2 V reference, right, because from here delta EFD is equal to Ka into V reference minus delta V1. So, you replace delta EFD, this delta EFD, right, and you will get in this form, this is equation 282, where A34 is equal to minus B32 into Ka is equal to minus omega 0 RFD upon LADU into K, this is equation 283, right. And from equation your 280, right, you will get that your, I mean from this equation, P delta V1 equation, from equation 280, right, you will get that P delta V1 is equal to A41 delta omega r plus A42 delta delta plus A43 delta psi FD plus A44 delta V1, but there is no omega r term in that, that is why A41 is 0, that is why here is written A41 is 0 A42 is K5 upon TR, A43 is equal to K6 upon TR, right. A44 is equal to minus 1 upon TR, B2 is equal to Ka into B32 is equal to omega 0 RFD upon LADS and into Ka. Just you put all these things, because each and everything if I write and all these things, it will consume more time. So, little bit you make it, right. There is no need to remember all these things, but you make it your what you call yourself, you do it. I am giving you the final one, right, otherwise it will consume lot of time, right. So, now complete steady state space model for the power system including the excitation system has the following form. So, if you write, it is now 4 into 4, we will come here only 4 into 4, not more than that. So, one is delta omega dot 4 steady variable delta delta dot delta psi f d dot delta v 1 dot. This is your A matrix, all elements are given delta omega r into delta 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 psi f d delta v 1 plus your b 1 0 0 0 0 b 2 0 0 delta T m delta v reference. This is equation 285. Now, with constant mechanical torque input, delta T m actually will become 0, right. So, with this, thank you very much, we will be back again.